Swayam Prabha. Digital India. Educated India.
See, so far we have looked at two different classes of excitation. One was applied from inside the shear layer and the other one was applied from the outside the shear layer. And we did as much as we could theoretically using those assumptions of parallel flow, all right. That implies that we neglect the growth of the shear layer, and we also looked at the linearized problem. Now onwards, what we would like to do is try to get out of the shackle of these two limiting assumptions and try to incorporate both the nonlinearity as well as the growth of the underlying shear layer. That is called the non-parallelism. So what is the way? Well, one of the way is, of course, you do some perturbation theory, relax some of this condition in a weak manner, and then you have weakly nonlinear theory and weakly non-parallel theory. Those efforts are really weak. That's what people found out for 20 years of further research, that those weak theories are really weak. We need to do something which should have adequate strength, and that is what we are now going to talk about. We are going to talk about investigating some of this problem, directly approaching to the Navier-Stokes equation and solving them. At the same time, we will still be doing those control experiments, and these are control numerical experiments. One of the things that we found out in the previous set of lectures is that if I have some kind of a free stream excitation, it does both. It creates a downstream propagating wave, and they can also give rise to upstream propagating disturbances. So there, what really happened, we did not talk about any specific length or time scale that was introduced from the free stream excitation. Today we are going to look at a problem where we are going to kind of specify both length and time scale. How do we do it? Well, we do it in the following way. We talk about vortices, a train of vortices, a large number of them. They are all equispaced and they are all going at constant speed, and they are also constrained to move at a constant height, so that we can take out some of the uncertainties of the analysis. So that's why we call it a controlled experiment. So we have each of the parameters in our control. I could vary this height, I could vary the spacing, I could vary the speed of convection. All these things are our parameters of study, okay? And that's what we need to do. Supposedly such a thing is happening over a flat plate boundary layer with a sharp leading edge, then what happens is the boundary layer grows from 0 thickness all the way downstream, which may actually, as Reynolds number increases, saturates. It does not completely saturate, but the growth can be neglected, and that's where we used our linear theory with parallel flow approximation. The moment that we want to simulate the flow past a flat plate like this with, let's say, very uniform free stream approaching the plate, a u infinity, then because this is a no slip wall and we are putting some kind of singularities out there, so what happens is these singularities will tend to create some induced velocity. So for example, if I talk about a particular vortex here and look at a point like here, so what will happen? This will create a velocity normal to that radial vector. So what happens is that gives rise to a wall normal component and a slip component. Slip component does not create too much of a problem, right? Because it is going to give existing fluid particle some kind of a slip velocity. However, the normal component is a little potentially dangerous, because that implies as if there is some kind of a mass source here, which is not to be there, because we are not explicitly adding any mass source. So what we can do is to obviate that conceptual violation of mass conservation, we can immediately talk about a image vortex system. The image vortex system would be nothing but its counterpart vortex, exactly at the same height, exactly at the same location. So what happens is at any point I could have a pairwise contribution coming in the opposite direction. One is in this direction, the other is in this direction, and you can see the normal component will cancel out and you will have a tangential component add up. And this is the whole idea of image vortex system. So then with this problem, then we can go ahead and solve this. What happens? We have seen that free stream excitation is capable of creating both downstream as well as upstream propagating disturbances. However, when we are going to compute, let's say, Navier-Stokes equation, what I could do is I could create a box like this. I cannot do the whole thing. This could be a semi-infinite plate anyway. So what we would be restricting ourselves with a finite size box. So that's the inflow of the box. Now, the top lid I have not specified. It need not necessarily be there. I could put it somewhere down below. Okay. And the outflow path, you notice that we have a very special layered structure. The hatched area indicates it's a buffer layer. What does it do? It basically does the following, that any disturbance that is going to be created and that will move downstream, when they approach here, that disturbance should cleanly go out. If it cannot go out cleanly, then there will be some kind of a reflection, and that reflection can build up and lead to numerical instability. So to discern physical instability different from numerical instability, we have to be very, very cautious in avoiding such spurious reflections. Okay? So what we could do is we could forcibly eject it out. That is possible, doable if we can. The other possibility is, of course, that we create a sort of a buffer layer where these oncoming disturbances will be attenuated in such a way that the reflected path will not be there, because we are decaying the disturbance coming in its full strength at the beginning of the buffer domain. Once it's inside the buffer domain, the amplitude will be decayed. So when it comes here, there is nothing to. So this is the concept of introducing a buffer domain. Now let's see what we are doing here. Well, what we are doing here is the following, that we have the plate here. The results that I am going to show you now today includes a domain like this, as we seen. This is our buffer layer, and there is a top lid. Okay, we have excluded the leading edge. We have excluded the leading edge. This is the inflow, and we have these vortices placed here, etc., etc. And we have seen the corresponding image vortex system will be like this, etc. That's what our image vortex system is going to be. So what is really happening in our computational domain the presence of this two vortex system will induce a velocity. As they are so far outside the boundary layer forming over the flat plate, and if we consider these vortices themselves to be some kind of an inviscid irrotational vortex, then the effect of these vortices would be to induce some velocity component. At each and every point, I will have a u infinity imposed and a v infinity imposed here. Right? And that quantity is figured out here, u infinity. Now, if you have followed what is done, the effect of irrotational vortices, you know you can use Biot-Savart law and calculate effect of individual vortex. Then the individual vortex effect could be integrated over the whole sequence. So we have a infinite array of vortices along with the image system, and that I could do it. You can look at the book by J.M. Robertson. The title of the book is, I think, Hydrodynamics. You can take a look at that book where this kind of inviscid vortex expressions are given. So this is basically the u component and v component of velocity as it is applied on some position x and y. Okay, all this sine hyperbolic, cos hyperbolic term comes because we are summing over infinite such arrays. What you notice that the gamma, individual strength of the vortex, comes into the picture. A is the spacing of the vortex, right? So this is your A. A is the distance between two successive vortex. B by 2 is the distance that we have talked about. Is the distance between, well, not this, sorry. This is the distance of this. Okay. This is that. And now what is happening, you can see these vortices are moving at a constant speed. So what I could do itself, I could see that individual location of the vortex would be given in terms of, say, the vortice's initial location minus c into t, because that's the speed with which it is translating. So this is your x bar, and those x bars are all out here, you can see. So wherever you position the computational domain end, so you know the x and y, plug in those quantities and you should be able to calculate the induced velocities at the box periphery. So that's quite easily done. So you realize also that there are two things. It's not only that u infinity, v infinity is imposed on the top lid of the computational domain, you also get it happening on the inflow too, right? So you have to incorporate those two. And here what we do is we don't use that induced component of the velocity. Why? Because what we are saying in the following is that this vortices impresses upon some kind of additional disturbances at the inflow and the top lid. As a consequence, some kind of disturbances will be created inside. They will amplify depending on the stability or instability of the problem, and they would like to go out. So here I don't want to a priori impose the condition that nothing has happened. We have to give some boundary conditions here which will be independent of what the inviscid flow is doing, because the dynamical system itself would evolve and create additional disturbances, right? So we have to give some interesting boundary condition that we are talking about, and we have already said that in this buffer region what we do, right? In the buffer region what we do is those disturbances plus this, all of the sum together will be decayed from some finite value to almost negligible value. Okay. Also, despite that, what we would also like to do, whatever may be the remnant should be allowed to pass out cleanly. So we'll talk about those boundary conditions shortly. Now, as I told you that x bar is some x minus ct, and then you saw that there the expression there was u infinity had some d in the denominator. Please note that d will never be equal to 0. So there is no such additional eigenvalues showing up due to inviscid excitation. So this is a proof. It is somewhat very interesting, because a similar such approach was taken by von Karman when he started studying the stability of the vortex street behind a circular cylinder. The vortex street that you get 2 rows of vortices, and in the original work of von Karman, he treated them as some kind of inviscid vortices and then tried to study the stability of the street. You realize that that may not be the correct way of doing the things. People have found out that's a wrong way. In fact, here also you see, when we have these 2 vortices, 2 rows of trains of vortices, the denominator term can never become 0, and then you don't get any kind of instability condition due to that. However, what we have seen that if we create these vortices which are at a distance a apart and they are migrating at a speed c, I can introduce a time scale. The time scale, which I will call it as Ts, would be what? Will be the length scale by the velocity scale. For this convecting vortices, the length scale is a, okay, and velocity scale is the speed of convection. So what will be the corresponding frequency imposed? So any point will see so many events happening per second, that is that frequency, that will be, I will call it as 1 over Ts. Okay. This is your physical frequency in hertz or cycle per second. What you could do is, from here you could create a circular frequency which will be nothing but so that will be nothing but 2 pi c by a. You notice that I purposely put a omega naught, because this is the fundamental unit, right? So if I have an infinite sequence of vortices like this, the lowest frequency is created by 2 pi c by a. Then of course you are going to get this superharmonics of it, right? So this is the way to then visualize the problem, that I would write down the disturbance stream function, which will be a function of x, y, and t. X, of course, dependence can be figured out here in terms of the phase I alpha x. Alpha itself could be complex because we are a priori talking about instability problem. What about the time dependence? Time dependence is going to be happening at omega naught and its various harmonics. So that's what we have done. We have put in there e to the power minus I n omega naught t. And omega naught, we have worked it out. And then we should sum over, because it's strictly periodic problem. You see, these vortices are strictly periodic. So it will not be a integral, but it will be a sum, and the sum will go on from n equal to 1 to infinity. Okay? And alpha, of course, will perform over the Bromwich contour. Now we all know what a Bromwich contour is, we can do it. So this is your expression for the disturbance stream function. Now, we also know that if we are trying to look at the wavy solution which is away from the exciter, then we should be looking for eigenvalues close to the origin. That is what we talked about, the Abel and Tauber theorem. So that's that. Then, having obtained this expression for disturbance velocity, and we have already written down the expression for u infinity and v infinity just now. Now what we could do is we could conjure a problem here that suppose I place this train of vortices at a non-dimensional unit of 20 or something, and I create some kind of a top lid which is slightly below. You know, my reason is that I do not want to include singularities inside the computational domain. It's a nuisance, you know. Any discrete inviscid vortices will work as a singularity, isn't it? So to avoid that, we keep those away, and our top lid is below that train, and then we can calculate the u infinity and v infinity. And if we calculate that, this is what we are going to see. This is shown with respect to one vortex. So that vortex location here has been fixed as the origin. And the example that we are seeing here, the gap between successive vortices is 100 pi. So it's about 345, sorry, about 315. And then you can calculate what is happening in the intervening period, right? So this is the vortex that we are focusing our attention upon. There is another vortex here at minus 315. There is another vortex here at plus 315. In between, this is the way the induced slip velocity is going to be. Immediately under the vortex, I am going to get the maximum, because that is the smallest, shortest distance, right? So that's what I get this peak. And you see, this is roughly about 0.08 for the height we are talking about. What happens to the v infinity part? V infinity actually flips sign. On the left hand side, I would have a positive. On the right hand side, it will be negative, right? Because it's rotating. So one side it's going up, the other side is going down. And that's what exactly you are seeing. Please note that u infinity and v infinity are of the same order of magnitude. It's only that here it is flipping sign. So it's going from plus 0.04 to minus 0.04. So this is about 0.08 range. And that is exactly like what you are getting. However, you note the streamwise extent over which the disturbance is felt. This is more localized. U infinity is more localized than v infinity. So what will happen? Of course, when you are looking at the Fourier transform of this u infinity, you will find a wider band. So basically what is going to happen is that u infinity and v infinity will excite different kinds of length scales. And that we should be able to see it if we obtain the Fourier transform. And that's what I am showing you. It's very interesting that the footprint of u infinity and v infinity means a lot when you look at in the transform plane. You know, this is one of the reasons that we need to be looking at all fronts. If I just simply look at the physical plane and say, oh, their relative magnitude is same, so they are having the same effect, In the transform plane, they are not so. You can see it very clearly. This is corresponding to u. So this is phi infinity prime. If I look at phi infinity prime, look at the maximum. Maximum is about 1. And look at the Fourier transform of v infinity, that gives us phi infinity. And that phi infinity, look at this, about 18. So you can see there is a order of magnitude difference between phi infinity and phi infinity prime. We'll use this information later. So please do remember, this is what is happening. This is why is it happening is you can also make out, because the v had a flipping of signs, and it did happen very abruptly, whereas u infinity decayed smoothly. That's why it has a wider band, but the 0, it does not peak up that much. Okay, so we have now characterized the input to the system, isn't it? So this is what we are giving it as an input. And we have talked about eigenvalues and the receptivity problem for both the wall modes, the modes that decay with height, and the free stream mode that grow with height. How are these two sets of modes linked together? This is something worth investigating. Let's see what happens. If I look at the Osmo field equation and the problem that we just now looked at, if we also create some kind of a wall exciter, then we would retain all the 4 modes, right? What is known to us is that if once you are outside the shear layer, these 4 modes have some kind of analytical structure that is given like this. We have seen that if real part of alpha and q are positive, then the first and third mode decay with height, while the second and the fourth mode grow with height. Okay, so this is something we should remember. And if we look at the consequence, then we can basically couple these two fundamental modes into a wall mode, C1 phi 1 plus C3 phi 3, which I will call it phi I. Okay. Similarly, I could call the other two as the free stream mode, which is C2 phi 2 plus C4 phi 4, which I call phi II. Okay. So basically, we need this phi II to match the imposed disturbance in the free stream. Okay. So if I do that, if I tell you what those disturbances are at the free stream, I have basically phi 2 and phi 2 prime in terms of u infinity, v infinity we just now calculated. So we can immediately obtain C2 and C4, right? So we can obtain C2 and C4 in terms of either using u infinity, v infinity, or phi infinity prime. So we should be able to work out. Why? What is happening in the free stream about this part? This part is subdominant. This does not exist. That's why. So independently we can fix C2 and C4 from the free stream condition, right? So this is what we obtain very easily. Now, having obtained C2 and C4, what we could do is also talk about two distinct classes of subproblems. You see, what has happened in instability theory, people suffered from some misconception. One of the misconception was, suppose I have inviscid vortex going in the free stream, there are no viscous effects. At what speed would it go? Your vorticity transport equation is the substantive derivative of omega equal to 0. That means what? The omega is going with the local speed. So that is what we call as the pure convection problem. So C will be equal to u infinity. Okay. If I do look at that, when C is equal to U infinity, then what happens? You have seen that this modes will coalesce. Why? Because if I look at the expression for Q, if C is equal to U infinity, then what happens? In a non-dimensional form, C equal to 1. So this part goes to 0. So then what you are getting here, Q is square root of alpha square. So what does it mean? Phi 1 and phi 3 are same, phi 2 and phi 4 are same. Phi 1 is, let us say, minus alpha, phi 3 is also minus alpha, because Q is equal to alpha and phi 2 equal to phi. So there is a case of mode coalescence. So this mode coalescence have to be kept in purview, and this is what we are talking here, that if we are looking at the pure convection problem, if the vortices move at free stream speed, then phi 1 infinity equal to phi 3 infinity and phi 2 infinity equal to phi 4 infinity. All of you convinced? If you are, then we can write down the free stream mode at the free stream. So I will write it as phi II evaluated at y equal to infinity, and that is nothing but your phi infinity itself, and that is given in terms of this. Now please note that because of the coalescence, we have C4 times capital Y times e to the power alpha capital Y, isn't it? Because this is the condition of coalescence. And then I can also differentiate it, and I get the corresponding value for phi prime II at y equal to capital Y. So now you see, this is these are the two equations, 7a and 7b, will help you in solving C2 and C4 in terms of phi infinity and phi infinity prime, right? So we know how to get this case solved. Once you have C2 and C4, you can do that. And as I also mentioned to you, when you look at the other mode, the wall mode, they actually go to 0 as y goes to infinity. So this do not interfere in the solution. So we get C2 and C4 like this. Okay. So here are your closed form expression for C2 and C4. Now suppose we have only the excitation in the free stream, then what happens to the condition at the wall? Condition at the wall should be one of no slip. So that means what? That means I should have the V component 0. That means I should have phi at the wall should be equal to 0, and I should also have U component 0. That means phi prime will be 0. So then if phi at the wall is 0, that is equal to phi 1 0 plus phi 2 2 0. Now what has happened? As far as this part is concerned, we at least know those multiplicative constants. But for this part, we do not know C1 and C3. So we are trying to clear out a strategy by which we can obtain those C1 and C3. So this is your condition for phi at the wall. You go ahead and write this as the wall boundary condition for the wall mode. That's what we said as capital phi of I. So that's your boundary condition. So that's why I have given additional subscript 0. And this I am writing it on purpose as phi subscript PC. PC stands for pure convection. This is the case we are considering with C equal to U infinity. So that's your pure convection problem. Then what is that? Phi I0 should be equal to minus of this, because sum of this is 0. So since I know this, I can put this. But you please note that we do not a priori know what this phi 2 0 and phi 4 0 bar are, but supposedly we can integrate something like our Orson field equation and obtain these fundamental modes. We should be able to get these right? Now, what has happened now? We have now two sets of equations to obtain for C1 and C3. So, this is what we are getting by putting phi at the wall equal to 0. So, this is coming from the free stream mode evaluated at the wall, and this is this. So, now what you are seeing, this is the v component of velocity and this is the u component of velocity. Whatever I did in the free stream, that in turn gives you this non-zero C1 and C3 from this equation. This is what we are calling as the coupling, that I am creating a free stream mode, but that is fixing the coefficient for the wall mode C1 and C3. So, you see, you have not created any wall excitation, but it is happening indirectly, right? Because of the free stream condition, we are going to get non-trivial values of C1 and C3. Once you do that, you get a bit of algebra to be done, and you get those C1 and C3 in terms of this, and the denominator is given in terms of this. And what is this? This is once again your y1, that compound matrix variable evaluated at the wall, right? But what we need to understand that in this case, phi 1 and phi 3 are the coalescing mode. So, this is slightly special. This is a special case where q equal to alpha. So, that is what we are going to get. And you also notice there are R1 and R2. Those are obtained here, R1 in terms of this and R2 in terms of this. So, basically this non-zero values of C1 and C3 can be now obtained in terms of C2 and C4, and that provides the coupling for this case. So, you can now understand what people hoped intuitively, that wherever possible I will excite the system. It will eventually create those eigenvalues. And here is a clue as to the coupling between a free stream excitation and the equivalent wall excitation. Now, I told you there are two subclasses of problem. One case we just now discovered or talked about is the pure convection problem. However, there would be a possibility that these vortices will not go at infinity, because this depends on the nature of the vortex. If it's not a inviscid vortex, then in its neighborhood I cannot omit the diffusion term. So, my governing equation is not necessarily this. For inviscid vortex, we had the governing equation as this, and that gave rise to C equal to u infinity. But suppose I talk about some viscous vortex, then even in a 2D framework, it would be like d omega dt should be equal to nu times this. And this per se will give you the condition that C will not be equal to infinity. For a long time, people in the stability theory fruitlessly argued in favor of this. If you look at all the publications till we came out into the picture, they always used to say, oh, C has to be equal to infinity and there is no receptivity. They also did not realize that there is a case of mode coalescence, etc. This is something we note. But more so, when we are looking at viscous vortices, then this is the order. I mean, C is not going to be infinity. And this mode of events occurring is what we are calling as bypass problem. Okay, so we are now talking about a case of convecting viscous vortices for which C is not equal to infinity, and that problem we are calling it as the bypass problem, implying that the convected vortices will not travel with the free stream speed. One can again calculate the boundary conditions corresponding to the wall mode, even though we are not creating any wall excitation, right? What we should be doing is we should be calculating the phi, which I identify with the subscript BP to indicate just a bypass mode. That will be capital phi I0. And now what you are getting, you realize that you have the modes are distinct. There is no more coalescence. And if the real part of capital Q is P, then this is the way that we are going to get, right? What we are doing here, we are again satisfying the free stream condition to calculate C2 and C4. Having obtained C2 and C4, they are here. This is your C2, e to the power minus alpha y, capital Y, into phi infinity prime minus p phi infinity. And C4 is this, minus of e to the power minus py within parenthesis phi infinity prime minus alpha phi infinity. So this is your C4, this is your C2. Now, this we are evaluating at the wall. So this is basically phi II at the wall, okay, with a minus sign, and that is equal to the wall mode at the wall. So this is what we are getting. So this equation that we have talked about created some kind of equivalent wall mode amplitude in pure convection and bypass mode when the real part of alpha and p are positive. If they are not so, we can change the condition appropriately and work out an alternative expression. So that's not a big deal. Now, what has happened here? We have calculated the effect of inviscid vortices at the wall. That's what we call as phi PC. Now, we have just now calculated if there are viscous vortices going, what is the equivalent excitation at the wall, which we call as phi BP. We can take the ratio, and it looks like this. Now, what have we used? We have used this condition. Do you recall I showed you how phi infinity was of the order 1, whereas of the order 18 to 20, whereas phi infinity prime was order 1. So we have eliminated that, and we have simplified this. So we can actually simplify it, and we get this condition. Okay. So what happens is you need to basically know what your phi 20 at the wall going to be for the pure convection case and the bypass case. That this ratio plus this. Now, what happens here is, of course, in general case, this is a small quantity, right? Phi infinity prime by phi infinity. So this part is negligible. So 1 plus alpha y, right? That's what we are getting. Y is usually large. We are taking it at a very higher up height. Alpha is rather small because we are looking at the eigenvalues close to the origin. So this is not really a very strong thing. What really determines this ratio is the ratio of the two. Okay, and what we find eventually that this quantity is going to be a small small quantity. That means this equivalent wall excitation for the pure convection case is a much weaker case than the bypass mode. Well, we can see this. We don't have to be convinced immediately because we don't have closed form estimate for this phi 2 0 bar and phi 2 0, but we can solve the Navier-Stokes equation and we can see what happens. However, we are creating the wall excitation by the free stream convecting vortices. But how would those wall disturbance go? This is something that we must distinguish, and this is where I think people have missed out the picture completely. And this is what we pointed out, is that well, a free stream excitation is equivalent to creating an equivalent wall excitation, but what should we track? Remember, in the earlier case when we are talking about Schubauer-Scamstad experiment, we created a wall excitation here corresponding to a fixed frequency, right? And then what we did plot the neutral curve in RE omega naught case for signal problem, and we found out the neutral curve like this, and the constant frequency disturbances were tracked by rays going like this. So this was your capital F equal to constant. That's what we studied, right? We've seen that. But now what is happening? Here the disturbance propagation is tricky because it is not happening at a fixed frequency. You have already seen that the moment I prescribed C and A naught, I created a sort of omega naught and its superharmonic. So this is not a monochromatic disturbance. What is invariant in this problem? It is the speed at which the disturbance is propagating in this free stream. All right. So what I could do is I could look at this and I could plot out the C equal to constant contours, and that is what you are seeing here. So this is once again in RE omega naught plane. The solid line indicates your neutral curve. It's unstable inside, stable outside, and these are various C equal to constant lines. So for example, this line corresponds to C equal to 0.3169. So these are all non-dimensionalized with respect to u infinity. So if a disturbance, if those convecting vortices go at this speed 0.3167, and if I try to trace them, I should be tracing them along this line. And this is significantly different than what we did for pure monochromatic wall excitation. Here I would probably be looking at this. And what you notice is basically that these lines are very square. For example, C equal to 1, that means when C is going at the free stream speed, that would correspond to C equal to 1 line. That is right there. And that remains always outside. So that's what people have talked about, that there is no receptivity to pure convection problem. So if you make some inviscid vortex go in the free stream at the free stream speed, the disturbances those are going to be created, they are going to be very, very stable, because you see this is so far away from the neutral curve. So this decay rate is rather large. So you are not going to create that. And this is what people have noted theoretically. But the point remains that experimentally it does not happen so. I mean, you know, free stream turbulence, etc., they all do have finite visible effect. So what are we missing? We are missing what we discussed today, that those vortices themselves did not necessarily be inviscid vortices, and then C will not be equal to infinity, and different values of C will have different instability pattern. See, for example, this case 0.3169. It enters the neutral loop here. So it becomes unstable here, and then it remains unstable for a long stretch. This is significantly different from this monochromatic wall excitation. There it just enters here, exits here. And now you see it enters here, exits there. But there could be even other cases where it would be actually going in and going in there. What more? If you recall what we have studied about the alpha I contours, this is alpha I equal to 0. Inside alpha is negative. How does it increase? We have the highest value of the alpha I contour is a line like this. So what happens is the disturbances, those convect with speed other than u infinity, they go inside, stays over a longer region, remaining unstable, and they also visit the unstable path and stay there for a longer time. So because of the prevalent mindset in late 90s, we call this as bypass transition. Why it is bypass transition? It is not really bypass, because you are still again creating waves. But what you are creating is a basically assembly of waves. You have excitation as omega naught, 2 omega naught, 3 omega naught. So in the end what you get? You get kind of a wave packets consisting of TS waves. We should not have called it bypass, but if we would not have called this as a bypass mode, how would we characterize it? We said this is not the usual Schubaugh-Kramster type of TS wave, but it's a different kind of TS wave, and we call this as a bypass mode of transition. But essentially these are wave packets, those are created like this. So this is what we must understand. And you also notice that there is a bit of a selectivity. There is a bit of a selectivity of the value of C. We see that this curve is something close to 0.26. So anything below 0.26 stable, anything above 0.4 also is stable. So there is a band. There is a band of convecting speed in which this remains unstable. In fact, some such experiment was done by Dr. Jim Kendall at Jet Propulsion Lab. So when I showed him this result in a conference in Washington, he actually narrated to me a couple of his papers where he's seen this thing but could never explain. And this figure very clearly says why he saw what he saw. I think I'll stop here. In the next class, I'll briefly explain what Kendall's experiment was, what he observed, how does it all gel with this. And you'll see a very interesting story emerging there.